So you've just tuned into a podcast. That means that the sound of my voice is exiting your speaker, entering your ear, and getting processed by your brain. Maybe later today you'll put on some music and the same thing will happen, though it might feel a bit different. For all that sound is and all it's able to communicate, physically, sound is really just pressure waves through air. These waves have frequencies and amplitudes, and the combination of all of these pressure waves in certain patterns gives us music and voices and everything else we hear. Today on our show, we're going to focus on the physics of music. What about certain sounds gives qualities of notes and tones? Why do different instruments sound different? And so on. We have a special guest on to explain this all to us, so stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. When I'm not thinking about science, I pursue a lot of other interests in a lot of other areas, but none of those interests are as central to my life as music is. In pretty much whatever free time I manage to find, I play music, I listen to music, and I think about music. It's frankly pretty hard for me to imagine being anything like who I am without music being a big part of my life. So I'm a guy who loves doing physics. I do physics for a living, and I love music. It's a big part of my life, like I said. And yet I never really spend a whole lot of time thinking about how physics and music interface, how the physics of music actually works. That is until a few years ago when I had some great conversations with my friend and colleague, Tim Cohen, at the University of Oregon. Tim is a physics professor there who works on things like particle physics theory and some cosmology and stuff like this. Basically the same sort of stuff that I work on. But he's also, like me, a musician. And in his case, he's an accomplished drummer. So he's a background in modern jazz and free improvisation. And Tim was telling me at that time about this class he was working on or just about to teach, I think, on the physics of music. And it just sounded amazing. Awesome. I just wanted to take that class and learn everything he had to teach. So for the sake of my education, and maybe some of yours, we invited Tim to come on Why This Universe today to talk with us about this interface between music and physics. Welcome, Tim, to Why This Universe.
Thanks, Dan. It's great to be here.
Great. So let's just start with a little background so people know what your story is, Tim. Let's do music and then physics. So how did you get interested in music?
I was always interested in music. My uncle's a professional musician. My dad's a great folk musician. My brother is a very accomplished saxophonist. So there's always been music in our house. Somehow I was drawn to the drums. My parents did everything they could to dissuade me from becoming a drummer, but that never works. And so eventually they acquiesced. I traded getting a bar mitzvah for a set of drums and been playing ever since. And then I have a bachelor's degree in jazz studies. I really wanted to go to school for music. And so my dad insisted that I also do something useful. And so I always say that the joke's on him. I became a theoretical physicist.
Yeah. No one's ever accused me of having a useful profession.
Indeed.
I think we were in Colorado, Tim, and we were hanging out. I think we were playing pool at that, Eric's pool hall, if I recall. And you were telling me about this class. You were either just taught it or you were just about to start teaching it, but you'd done all this research and planned all this stuff. Tell me about this class you created on the physics of music.
Yeah, so this is a course that had been taught at the University of Oregon for many years. It was a class for, we call them physics for poets classes, right? Where it's meant for people who have no background in physics, who are terrified of math. And so really just a conceptual course. And I had gone into this knowing for sure one of my main messages and then having a sense of a sort of second set of messages that I knew almost nothing about. So the main message is there was a question that always bothered me as I was growing up playing music and especially getting a music degree, taking music theory courses. And it kind of speaks to my sort of fundamental physics interest, which is the fundamental building blocks in music are that we use this 12-note scale. And I wanted there to be a reason for that. And especially because it's multicultural. Different scales, of course, exist in different cultures. And there are certainly examples of cultures that have microtones. But overwhelmingly, human beings have been drawn to these 12 notes or some subset of them. And so I was kind of aware of that. And I really wanted to understand why. And there is a good reason. So that was one of the main messages, just because that revelation had been so important to me. And the other message I wanted to send was just the idea that musical instruments are physical systems, and that we have simple models for how they work. Actually, in working on the course, I was shocked by how little we actually understand about in detail how instruments work, how they make sound. But I learned some absolutely fascinating things, even in the sort of, as physicists like to say, the spherical cow model of the instruments. There's already, even at that level, some really interesting things that I learned, and the way the ear works and the way perception of sound works, these kinds of things. So that was kind of the second half of the course, was more about the physics of making sound and ingesting sound, as opposed to the more theoretical aspects of why we construct music the way we do and so on.
All right, so talking about different instruments and the sounds they make, I actually remember asking a question when I was, my first quarter of college, I think. So I'm a brand new college student. Like you, as a music major, I ended up doing physics later, but I started out studying music. And I didn't know any physics at all. And I asked one of my professors, if I play a middle C on a piano and I pluck the same note on my guitar, they sound different, but it's just the same pitch. So why are they different? And he gave me some answer, which I think is just circular, the timbre of the instrument's different, which is just a way of saying that the instruments sound different. It wasn't really an answer. So what in your physics of a music class, how do you answer that question?
Great. So the spherical cow answer is that there's a set of ideas called the overtone series. And basically that, so music, when we talk about a note, the most abstract representation of a note is just a simple sinusoidal wave, and it has an amplitude and a frequency. And there are even tone generators, you can easily Google and you can hear what a sine wave sounds like. It's a very pure tone.
If you hear that, will it sound like a musical note to the?
Oh, absolutely. Yeah. You would recognize the pitch. You could sing along with it.
Okay.
But the reality is that musical instruments that have a pitch, they dominantly produce that frequency. They also produce a whole series of other frequencies. And it's that combination of all of those subdominant frequencies that give an instrument its timbre. There's a sort of, again, a kind of simplifying way of understanding that, which is there's this idea of the overtone series where, any real physical system is going to have its dominant frequency, but then it's going to have these subdominant frequencies that have more nodes. Like a guitar string is kind of the simplest example. You pluck it and it's mostly going to give you the biggest oscillation just up and down between those two pegs. And that actually up and down motion excites air molecules, which hit your ear, and you hear that frequency of that motion. But there's also a lot of other wiggling going on, again, where the two endpoints have to be fixed because they're fixed on the guitar. To a very good approximation, actually, of course, on the guitar, right? Things wiggle around even at the endpoints, certainly at the head joint, right? And so all of that stuff feeds into what makes a particular guitar sound the way it does.
So is there an example of if I wanted to get the purest, note without any of the overtones to whatever extent possible, is there an instrument I should go to? Is there an instrument that mostly produces that pure tone? And in contrast, are there instruments that have maybe more pronounced or richer overtones?
Yeah. So my understanding is that the reason that the oboe is used in orchestras, the oboe sounds a tuning note and everybody tunes to the oboe, is because it's the closest to a sine wave.
Oh, okay. All right.
Yeah. And at least in the orchestra. And certainly the drums are the messiest systems as far as this goes. But even like drums that are tuned to a note, like a timpani drum, have a very rich overtone structure, but you can definitely hear a pitch there, but also there's this very rich resonance that happens because of the shape of the drum and
And this is why drummers aren't usually the ones playing the melody, right?
Indeed, yeah.
Right. Yeah. Okay. Okay.
Yeah.
Good.
Although there's this insane person. His name's Ari Honig. He's an amazing jazz drummer, and one of his shticks, I'm sure you can find all kinds of YouTube videos of this. He plays jazz drum heads, melodies on the drum set. You can recognize them. He pushes a lot into the heads to change the pitch. Anyway, so even then, there are some of these some people who take these ideas to the limits. He's a great example of that.
So let's turn next to like intervals and scales and things. So you mentioned this before. You were talking about this 12-note scale. So from a C to a C on a piano, there are 12 black and white keys. Like, where does that come from? What's the physics of that? Are there alternative ways we could have structured various combinations of pitches or frequencies we could draw from to make sonic art?
Yeah, so great. So like I was saying earlier, that was this question that really bothered me when I was growing up. And the answer is kind of an accident of number theory, or just of the properties of numbers. And I guess the properties of human perception. So the most important fact is that when you say going from one C to the next C on the piano, that concept of the octave, where we hear those two notes as being the same pitch, those notes differ from each other by a factor of 2 in their frequency. And that's a property of the ear, right? That's just the way humans perceive notes. We identify those notes as sounding very similar, and it's for a natural reason. That's the way the ear kind of functions. It's for people who know what this means, it's logarithmic basically. So the ear hears in log base 2, and so it hears those two things as being the same.
Like why we call one C the same note as another C, it's not actually because of they're the same anything in real life. It's just that the higher C has double the frequency of the lower C, and we perceive those as the same.
That's my understanding, yeah.
Two things that we call an octave, the fact that the higher frequency one is exactly twice the frequency of the lower frequency one, like that's a built-in thing to the laws of physics or something. But the fact that we think of those two notes as having something in common, what we call the octave, that is something that has to do with the physiology of the ear and brain or something.
Yeah, exactly.
And we don't do this with other stuff. We don't say that the wavelength of a red light has something to do with something with twice the wavelength or half the wavelength. Like we don't think of those as having anything to do with each other, but we do with sound for some reason. That's interesting.
Yeah, I not to digress, but my understanding, and actually I was looking into this a little bit this morning, there are two different theories of hearing, and at least according to Wikipedia, the prevailing understanding is that basically both are at work in the brain. But the one that I taught when I taught this course, and the one that I think speaks to why the ear perceives the octave this way, is what's called the theory of place, which is that your cochlea is this organ inside your ear, and it responds to different frequencies in different places. And just the way it happens to respond has this same kind of structure, so that it kind of doubles, right? The length, when the frequency doubles, the position, I think, moves roughly. And if you look at this up, you'll see it's quite a wide spread. They have these pictures where there's a range of frequencies affect different regions, but that plays into, I think, a big part of human perception of sound. So it's the fact that it localizes in a position, I think, is, and then our brain perceives that in some way.
So it's possible that like the two different C's are localized in the same part of the cochlea. Well,
I think they're localized in different places, but I think it has to do with the ratio of the distance between where they are. By the way, I should have said up front, I mean, I'm far from an expert in any of this, so this is just what I gleaned from.
I'm learning a lot, Tim. This is great.
So I'm sure on the comments, experts will chime in and tell us if I'm completely off base here. But yeah, that was my understanding of how the physiology played into this perception. So back to scale building, we have this concept of the factor of 2 being important, and then there's another very important ratio. This goes back to Pythagoras, which is basically the ear really likes to hear perfect ratios. So if you have a whole number fraction, like 3 halves, then the ratio between, if you play the note 1 frequency and then you multiply by 3 halves, that is a very pleasing sound to the ear, those two notes together. And that goes by the name, the perfect fifth. So like if you're playing a C and then you play the note G, that sounds it actually sounds almost hollow. When in music theory class, when we learn to do ear training, we try to kind of hear these different sounds and characterize them. And often that's characterized as a hollow sound because it's almost like hearing the C. And that's because they have this nice simple ratio in frequencies. So those two facts together basically explain the 12th note scale. There's a very important concept in music theory. It comes up especially all the time in thinking about jazz theory, which is called the circle of fifths. But I think it's pretty universal in the way most musicians think about music. And the point of the circle of fifths is that if you keep doing this operation of taking the frequency and multiplying by 3/2, you keep going up in this ratio of a fifth, you can play this game. You can just keep going around. You can, what they call, go around the circle of fifths. You just keep doing this operation. You go up a fifth, you go up a fifth, and you keep doing that. And eventually you get almost all the way back to where you started.
Yeah, that almost carries a lot of weight here, right?
Exactly. That's the whole thing, okay, is that there's an accident. This is the accident of number theory.
Right.
And the accident comes to this very esoteric idea of what we call temperament in music. So temperament is basically a strategy for choosing exactly what frequencies you want all the notes of the 12 notes to be.
How you want to tune your piano.
Exactly. It's how you tune your piano. And if you build a scale by doing this game of just going up and up in fifths, the frequencies that you would get are slightly different from what you would get if you use what's called equal temperament, which was invented by Bach in order to solve some major problems in clashes of tunings and stuff, to make life a lot easier if you want to go change from key to key to key. So the idea of equal temperament is we take the interval of the octave, which is a perfect factor of 2, and we divide it into 12 parts. Why do we divide it into 12 parts? It's because this game of going around in the circle of fifths, we get almost back to where we started if we go around 12 times. And by the way, when I'm saying this, keep in mind, of course, as you keep going up in fifths, you're going to change octave. So every time you change octave, you should divide by a factor of 2 to go back.
Sure. And I'll just add one thing, too, is if you divide that octave up into 12 equal pieces, along those 12 steps, you will not only hit all the notes in major and minor scales, but you'll hit the perfect fifth, you'll hit the major third, minor third, all the sounds that we have in Western music, you'll hit along the way by breaking that, or at least you'll almost hit all those notes by doing that, right?
Exactly. That's exactly the point, is that the equal temperament, if you just want to say, I know I like this 12 notes because of the circle of fifths, what you would do, what Bach did basically, is he said, well, let's just equalize the distance between all of these. And the way to equalize it on the logarithmic scale is to use the 12th root of 2, right? So just like we have this concept of square root, you take the 12th root because you know you want 12 steps. And if you multiply the 12th root of 2 12 times, you get a 2. That's its property.
Did Bach actually know all this? Did he know about sine waves, and did he know about frequency and hertzes or something?
That's a great question. I don't know if he just did this by ear, because the idea of equal temperament is that the problem was at the time that every key, so if you're in the key of C or you're in the key of D, if you don't have equal temperament, then the ratios between all the notes are slightly different.
Right.
And so the invention of equal temperament, however he came to it, I don't know.
Okay.
But the invention of equal temperament was to make it so that you could change keys and that all the ratios would be maintained. Because Bach loved to change keys, right. And arguably he invented, modern Western music theory. And in fact, when you take music theory courses, you learn to write Bach chorales is a huge part of the education. And
I've written my share of them.
Yeah, exactly. He really understood these rules and kind of codified them in a way that makes them really accessible and easy to understand and learn. Okay, so the punchline is, if I take the equal temperament sitting in front of a piano and I start on C, then the major scale is just the white keys. But I've got extra keys there. I've got the black keys. So what the 12th root of 2 does is it takes me from C to C sharp, right? From the white key up the black key. And so every time I multiply by the 12th root of 2, I go up one of those so-called half steps. So to get to a perfect fifth, if you go sit in front of a piano, you can count, takes me 7 steps. Okay? So now here's the accident of number theory finally. 2 to the 7 over 12 power is 1.4883 plus, infinite series.
Awfully close to 1.5.
Well, 3 halves is 1.5, exactly. And so the little adjustment between those two things is all of this business of temperament is all about, do we want to make the perfect interval sound perfect, or do we want to make the temperament equal so that when we change among keys, everything stays quite sonorous?
If I'm hearing you right, Tim, what it boils down to is I've got a C at a particular frequency, and I want to know on my piano how to tune the G, which is the fifth. If I'm using a equal tempered scale, then I have to tune it to 1.48 something times the frequency of the C. But if I wanted it to be a perfect fifth, then I would tune it to 1.5 times that frequency of that C. So there's like a different schemes you could use to constructing the notes that you're going to make music with.
Exactly, yeah. Although I had a great piano tuner when I was living in Oregon, and I talked to him about his tuning method and temperament, and he was one of these guys, been doing it forever. He tuned by ear, and he told me that actually as he goes up the piano, it stretches. Because of what we were talking about earlier, with the fact that the piano has all of this rich overtone structure, he basically tunes it by ear, looking for the intervals to be exactly right with whatever happens with the feedback of the piano and the soundboard in the piano, as opposed to like sitting there with some kind of meter. And so I think actually piano tuning is one of these incredible art forms that is completely unappreciated.
I would have just guessed it's just a matter of measuring it with a tuning device and moving on. But yeah, you're right. There's a lot more you could do with it.
He told me that if you did that, you would be very unhappy with how it sounded.
Huh.
That was his claim. We had this whole conversation. Yeah, I was fascinated watching him one day. And
so if I go to a music store or whatever, anywhere with a piano, it's certainly tuned to some sort of equal tempered scheme. Tim, have you ever played one that had like pure intervals, perfect intervals?
I've never played one, but I found some examples online.
How does it sound? How does it make you feel when you hear it? There's
some definite weirdness. You can hear, especially if it's a piece where they're trying to maybe emphasize the difference. Yeah. It's something's kind of funky.
And I'm sure a composer would write music differently if they knew these were the notes they had to work with.
Exactly. For the listeners, if you go Google this stuff, you'll find there are a bunch of nerds out there who are into all kinds of different temperaments and will argue about this kind of thing endlessly, what sounds the best. And then, I think modern composers then play with these things. Because of keyboards make it very easy. You can just program a temperament into a keyboard. But one thing I did in my course is I sat down with a program very familiar to physicists, Mathematica. Mathematica has a tone generator feature. So what I did for my course is I basically did the exercise of constructing the scale, the 12 notes by multiplying by the 12th root of 2, and constructing the scale by doing this thing of multiplying by 1.5 every time you go out of the octave, divide by 2 to bring it back in. And then I played the two against each other. And when you get to the final C, there's some weird stuff that happens in the middle. And of course, you have to remember, it doesn't just get progressively weirder. The difference is because the scale constructed by going around the circle of fifths kind of jumps around.
Right.
But by the time you get to the end, the two C's against each other sound pretty raunchy. And in fact, there's again, for people who are familiar with this phenomena, there's something called beating that happens. When you put two sine waves that are very close in frequency on top of each other, you basically get superimposed one big overarching frequency and then a much shorter wavelength beating frequency. And you can hear that very distinctly. Oh, yeah. And from my research, I found that this was called the wolf C, or the wolf octave, when you put these two things against each other, because it howls like a wolf.
So here's a question I have. We've talked a bit about how the same note will sound different on different instruments, thanks to having different timbres and overtones and stuff like that. But also, even just taking a single sine wave, we could play the same straight note with a slightly different shape, right? Like a square wave or a triangle wave, for example. So can you explain why that sounds different to us?
Yeah, it's the same, exactly the same idea. Those are really great examples of this phenomenon of building quality of a tone by adding many, many different sine waves together. Some of your listeners may have heard of the idea of a Fourier transform. And a Fourier transform is just a mathematical procedure which basically lets you take a shape like a sine wave, and you do this process called the Fourier transform, and what it spits out are the frequencies involved in that shape. So for a sine wave, say it has frequency 100 hertz, you'd apply the Fourier transform, and what the Fourier transform would spit out would just be that you have one frequency, 100 hertz. For the square wave and the triangle wave, you do the Fourier transform and you see that they, I guess the square wave is quite complicated. Again, if you look, there's some beautiful stuff on Wikipedia, some animations. You can look at the, one of these animations has adding more and more and more sine waves to get this square, this very sharp square shape. And actually, you know that the square wave requires a really non-trivial number of sine waves because it has a sharp discontinuity, right? It has this literal square shape where it has a corner, whereas sine waves are all smooth. And so in order to get that sharp feature, you actually have to add an infinite number of sine waves. So that same idea and those different waves have characteristic sounds. They sound a little crunchier, whereas if you go listen to a sine wave, it'll be really kind of a smooth sound. So in these courses, we often talk about exactly this thing. We Fourier transform the signal, we look at the oscilloscope, and the difference in the oscilloscope is giving us the difference in timbre, and that's explaining it's this different combination of sine waves. Every instrument has its unique combination.
Tim, I have one more. I want to back up a little bit and ask one more last question about temperament and intervals and stuff. So, the more I appreciate that there are these nice mathematical ratios that are pleasing to the ear, and that our scale doesn't actually hit those notes or those intervals exactly, I have to wonder, like, is this why guitar players bend strings? So on a guitar string, if you push a string perpendicular to the length of the neck, it will effectively make the pitch go up. So, maybe I put my finger on a certain fret and I hit the note, and then I pull that string either up or down, and it makes the pitch go up. But but this allows me to kind of adjust the pitch of the note continuously. So on a piano, I mean, if I'm hitting a C and I want a higher pitch, all I can do is go to the C sharp. Like, there's nothing in between. On a guitar, you can hit any pitch in between by bending the note, allowing you to kind of get frequencies between the frets. To me, as a guitar player, it's very instinctive to bend strings. I don't necessarily bend them to exactly one semitone or 1/12 of an interval or octave. I bend them in varying degrees, and I don't consciously think about what degree of bending is going to work. I just do what sounds good. I wonder if in some way am I trying to get to some sort of perfect intervals as opposed to my, equal temperament scale.
Absolutely. I think that as a music appreciator, to me, some of my favorite moments in music are even when people bend the pitch and they go somewhere kind of gnarly, right? And so I think that great musicians have this intuition for playing with the tension and release of exactly getting to those perfect intervals and then pulling away from them a little bit. And that's it's just an extremely effective musical device that, as you say, piano players don't have access to, but most other instruments do.
Right.
And it sends chills down your spine, right? I mean, when someone does that super effectively.
So, Tim, we've talked a lot about, intervals and notes and frequencies and things, but we haven't talked about rhythm really much at all. I'm wondering what kind of things you say in your course about the physics of music that might pertain to this important aspect of music.
In rhythm, certainly in the way we think about Western music, we set up some kind of pulse. And then the idea of rhythm is always just how do you either include many of those pulses in a note or subdivide that into smaller and smaller intervals. Typically we divide by 2 or by 4, but we can also so when we say take the pulse, divide it by 2, we often call those the eighth notes, or by 4, we would call those the 16th notes. You can keep going. There's 30-second notes, but if you divide again. But we also play with, say, dividing things by 3, where things get a little more interesting, and often that makes you feel a little off kilter. If you've got a pulse of 4 going on, and then you start putting subdivisions of 3 on top, they only fit together every so often, every 12, right? And so the way you choose to sort of shift those 3s around can be extremely effective musically, and playing the 4s against the 3s and all of this kind of stuff are often great musical devices.
I guess it could all be boiled down to number theory once again, right?
Exactly, yeah. And I think, at least to me, also being a drummer, it's kind of a more obvious. The connection to the number theory is sort of in your face with rhythm, because you're always counting, you're always dividing, whereas the connection with pitch is a bit more abstract. And so we spent a lot more time thinking about pitch.
So Tim, I have one final question for you, and this is actually about something we talked about all those years ago in Colorado. And it's more of a personal question, but like when you are in the act of either composing music or performing music, do any of the things you know about the physics of sound or the physics of music come into play? Are you thinking about those things? Are there things you learned in contemplating how the physics of sound works that inform how you create music? Or are these just completely separate intellectual pursuits for you and your relationship between music and your relationship with physics?
I would get a version of that question a lot, especially when I was an undergraduate. I would tell people that I was majoring in music and physics and math, and they would ask me, "Oh, there's so much math in music. Those things seem so related." And I always kind of rejected that notion. To me, I felt like especially the performance of music, and the way, in jazz and improvised music, especially, the idea is kind of to let the intuition take over, to really, when you're really in the zone, your ear, the ideal state is that you're just hearing and responding to what you're hearing, and that you're completely immersed and doing no thinking. To me, I always felt like, as an undergraduate, I would feel like these two things were really quite separated in my brain. Over time, especially as I got more involved in research, which is what happens when you go do a PhD, I find that there's a lot more connection between my relationship with music and my relationship with physics than I had appreciated all those years ago. But again, has nothing to do with number crunching. And it has everything to do with the concept of being in the zone. When you're, yesterday I had a surprising multi-hour block of free time, which I'm sure, as you can appreciate, Dan, never happens for those of us academics. So I had an afternoon where I could sit and do a calculation, and the 3 or 4 hours just flew by. Turned out, of course, I did the whole thing wrong, because I had the wrong starting point. My Feynman rules I derived wrong. Nonetheless, it was a blast. I was there. I was in the zone. I worked my way through this calculation, and I really had this very satisfying experience by the end of it, which has a lot in common with the way I feel after a really good practice session. So somehow when you're really like absorbed into what you're doing and it's kind of flowing, I feel like there's a lot going on that's really in common in the two disciplines for me. Another aspect where I've realized that being a musician has played a huge role in my physics career, and honestly is probably a part of why I've been successful, is that both in teaching and in giving lectures on my research, which is a big part of what we do, I've found that the fact that I have spent countless hours performing on my instrument led me to have zero stage fright and to feel extremely relaxed and natural on the stage. Now, that's not to say that I'm not sometimes very, very intimidated, but that's kind of a different feeling than knowing that I have the confidence to stand there, to perform, and in particular, as a jazz musician, to improvise, that I have all of this experience of stumbling in front of people, of doing something that sounded terrible and rescuing it. And the same skill set really plays a surprisingly large role in my performance as a physicist. And I find that my background in music has really influenced the way that I lecture, the way that I give talks, and the way that I communicate about physics.
Okay, so before we log off, are there any things about the physics of music that you found to be particularly surprising?
So one of the most surprising things I learned in preparing this course was when I was investigating how various instruments make sound. The guitar is extremely intuitive. You can see the motion of the string and it, translates directly into the sound you hear. So typically we start with strings that have fixed boundary conditions where the two ends are attached. And then we generalize that idea to pipes, to columns of air. And again, we're all pretty familiar with that. We've all banged on pipes and know that they come with a fundamental tone. And, again, once you have this intuition for strings and the fact that you can have the dominant frequency, but also you can divide it more and get these sub frequencies. For the students, it's pretty intuitive that you can get different notes out of pipes, and especially as you change pipe lengths. But the thing that I learned that I found completely shocking, that I'd never considered before, is how does a flute make sound? So flutes are arguably the most primitive of the instruments besides the drums, really. And they turn out to arguably have the most complicated physical mechanism for producing sound. So it turns out that, what's the idea of a flute? You blow over an edge, right? So even like very simple ancient flutes where you just have a series of reeds and you blow over the edge of them, right? That gives you this nice, this beautiful flute sound. Modern flutes have this hole that you blow over, not into. Everybody who's tried to play around with a flute knows it's actually hard to get a sound out of it. You blow into the hole and nothing happens. You have to blow over the hole in just the right way. So it turns out that what's happening is there's this very complicated fluid dynamics process that's going on, which is that you're providing basically a constant stream of air, and some of the air is going into the flute. And as that happens, you're changing the pressure of the air that exists inside the flute. And so it starts pushing back. And eventually as you're blowing in, there's so much pressure that it actually pushes your airstream to go out above over the top of the flute. So there's this back and forth motion. That's where the waving comes from. That's where the sound generation comes from. It's an effect of turbulence, actually, that there's this feedback from the air inside the flute, and it's causing your airstream to go over and in this oscillating pattern. And so that's a very turbulent process, and it has a lot of frequencies involved. It has a lot of overtones. It's a very wide signal. And then when you push down the keys and you change effectively the length of the flute, it picks out dominant tones, and that's where the different notes come from, is they're basically isolating different components of this very complicated input.
I had no idea. And prior to this, I just thought of a flute as like an organ pipe, right? It's not at all. Okay, that's super interesting.
Exactly. And so organ pipes, I think it's the same phenomenon, because they have the little notch and they blow air across that notch.
Oh, okay. So
I think they're just fancy. I think they're like flutes in the same way.
Okay.
It's a saxophone or so a saxophone, for example, is much simpler to understand because there you like have the reed buzzing in the mouthpiece, right? Again, it's providing a broad spectrum, complicated signal that you're then kind of focusing out with the keys on the saxophone. But there, the tone generation is much more intuitive. At least it was to me.
Huh.
And so anyway, that was just one of the favorite things I learned in researching for this course was, and I loved the fact that, again, that it's one of the most primitive instruments and physically it's one of the most complicated.
Right. Made by people who couldn't possibly have known about the physics, but yeah, that's great.
Yeah, absolutely. There's another fun little music instrument design feature, which people may not appreciate. So there's the saxophone and the clarinet. People who have played these instruments will know this. The clarinet is a just straight cylinder with keys on it. And then it has the mouthpiece and the reed attached to the mouthpiece. So again, you blow into this reed, it vibrates, it makes, and that creates the initial pulse. And then when you play the keys, you change the length of the pipe, and that picks out a dominant frequency, which is the note we hear. So both instruments, the clarinet and the saxophone, they have what's called an octave key. So the thumb close to the mouthpiece pushes this little key that opens a hole very close to the mouthpiece. And it's called the octave key. I think it's called the octave key on the clarinet too. But on the clarinet, what it does, it doesn't make all of the notes sound an octave higher. It raises the pitch by the interval called a 12th, which is 19 half steps. And so clarinetists have this incredible mental gymnastics that they have to do, which is that they actually have to know two sets of fingerings. They know all the fingerings for the notes without the register key pressed. And then when they press the register key, the notes all move around. They move up by this factor. And so they have to learn how to, map between the notes they're seeing, the higher notes, and a different set of fingerings, which I find to be a completely mind-bending thing. I don't know how they do that.
I didn't know that. Okay.
The saxophone, yeah, isn't that cool? On the saxophone, the octave key really literally pops an octave. And that's because the saxophone is a cone shape. The saxophone was developed much later than the clarinet. And again, as I understand it, I'm not a historian. The saxophone's invention, there were two main things that Adolphe Sax did. His two innovations were, one, that he used brass, so it was much louder than a clarinet. But the other thing was that he gave it this conical shape so that it was a lot easier to play. So you just hit the octave key and you actually go up an octave and you have all the same fingers.
Right.
So I thought that's a great physics and music thing, is that you can use the fact that it gets wider as it goes down leads to this phenomenon of this difference in what that key does.
If people want to listen to your music, Tim, where do they find it?
Oh, I have a couple of records on Bandcamp. My brother has a record label called Eschatology Records, and we have a few things there. And then I have a band called Cage Match. It should be pretty easy to find if you Google that. We have a couple of records. And
I've only listened to one of the records, but I really liked it. So this is the one you did with your brother. That was great.
Yeah, we have a duo record, and then we have a record with a guitar player that's more recent. That's really fun.
I'll check that out.
Why This Universe is brought to you by the University of Chicago Podcast Network. Our show is produced and edited by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of physics and astrophysics at the University of Chicago and Fermilab. The song you're hearing right now is Don't Panic by Tim Cohen. If you like our show and you want to support us and you want to get access to exclusive Ask Us Anything segments that we host monthly, you can join us on Patreon for as little as $3 a month, and your support helps us keep creating new episodes. As always, thanks for listening.